In my last video, I gave the globe believers back their fantastically huge sun, meaning that Bill and Jane could each see almost half of the sun from the terminator line on opposite sides of the Earth. Neither of them could see the black line in the middle of the sun because it's blocked by the Earth they're standing on. Then I zoomed in on this area and added the moon dead center of the black line and asked if Bill and Jane would be able to see that peaked new moon from those same locations. Now it stands to reason that if Bill and Jane are unable to see the black line, then they couldn't see anything within the black line either. As expected, a lot of ballers appeal to refraction to one extent or the other. But before I address refraction, let me address dip angle, the second most common rescue device. Ruhif writes, yes, you can see the center point of the sun from antipodal points. That's because the two horizons are not perfectly parallel. You have to assume the two observers are at least standing up. If you're at the terminator line, which is 3,959 miles from the center line, and the sun is 93 million miles away, then you would need to be looking down at an angle of approximately 0.02 of a degree below perfect eye level to see the center point. You only need to be a few feet above sea level for the dip angle to the horizon to be larger than this angle. Even at a viewer height of 6 feet above sea level, the angle to the horizon is about 0.04 of a degree, geometrically speaking, which is far greater than the angle you need. You're welcome. Slow down there, Ruhif. I haven't thanked you yet. In fact, it's clear that you are new to this sun and moon angles discussion and haven't seen my earlier videos. The first video I put out on it back in February exposed the very premise you bring up now, since my argument has to do with the incongruent angles to the sun and the moon. First, you appeal to something called dip angle, which is the claim that we look down to our horizon, and would certainly be the case if we lived on a ball. Not only that, but the horizon would drop lower and lower the higher we climbed. Of course, this is refuted by everyday observations made by millions of people who have never seen the horizon be anywhere except eye level. It's also refuted by every artist in the world who has even a cursory understanding of perspective. These first two examples are from Brigham Young University, but you can easily Google vanishing point in art or horizon in art and find hundreds of artists explaining that the horizon line is always eye level of the observer. As you can see, every one of these equates the horizon/vanishing point with eye level. I especially like the lower left one, where the artist imagines himself in the picture and places the horizon line where his eyes would be. For those who don't quite get what Ruhif is saying, he's making a claim that the angle at which a person can see the horizon is greater than the angle at which they could see the sun, and therefore we should have no problem seeing the sun from the terminator line. So let's apply that theory to the real world. Live science tells us that for a 6-foot-tall person, the horizon is a little more than 3 miles. They even have the picture of the guy looking down over his dip angle and seeing around the curve of the Earth. Of course, Taboo Conspiracy and Wide Awake have utterly destroyed this 3-mile horizon claim over and over. But we'll go with it this time for argument's sake. We know that left to right in this photo is much more than 3 miles, right? So let's put Live Science's dude out on the sea, apply the dip angle, and see how it looks from the side. Now we know that dude's horizon will actually rise up to his eye level, but Ruhif specifically stated he's talking about geometrically. And geometrically speaking, there is indeed an angle from dude's eyes to his feet level 3 miles away. But then what? Are we supposed to believe that this red line will then allow him to see around the curve of the ball Earth to the sun? That's what ballers just can't seem to grasp. If the ship is disappearing over a curve on the y-axis at 3 miles away, then the same ship is disappearing on Science Live Dude's y-axis at 3 miles away too. And his y-axis is our x-axis, and we'd be able to see the curve that's hiding the ship from Science Live Dude. But Mike, you say, the angle to the sun is only a little more than 0.02 of a degree, remember? Okay, but do you remember this guy?
And what you're seeing here is a mirage.
Did you know that at an eye height of 10 feet and a distance of 55 miles, the angle to the shoreline of Chicago is less than 0.02 of a degree? So if Bill's terminator line is on the Lake Michigan shoreline and he can see the sun due to the dip angle, then he can also see the entire city of Chicago all the way down to the lake shore, because the angle to the shoreline of Chicago is less than the angle to the sun. What Ruhif seems to be missing here is that the 2/1000ths of a degree to the sun is 2/1000ths of a degree below the horizon. And since the horizon is the lowest possible point we can see, it wouldn't matter if the sun was 1/100000th of a degree below it, because we can't see any fraction of any degree below the lowest point we can see. And to make matters worse, all of this dip angle stuff is irrelevant, since I've already granted the bigger than all outdoors sun, and that both Bill and Jane can each see practically half of it from their positions on the terminator line. What I'm asking now is if Bill and Jane can also each see their respective half of the peak new moon at the same time. And just so you know, Ruhif, the angle to the moon is 9/10ths of a degree below the horizon, as compared to the sun's 2/1000ths of a degree below the horizon. So the question is, can Bill and Jane each see both objects on their horizons at the same time? And as my first angles video all that time ago pointed out, if you allow that Bill and Jane can each see 2/1000ths of a degree below their horizon to see the sun rising or setting, they can't also see the moon. On the other hand, if we allow that they can see 9/10ths of a degree below their horizon to see the peak new moon rising or setting, the sun will be up in the sky, far above their horizons. 3.22 sun diameters up in the sky to be exact, as determined by both mathematics and a real-world 2-scale experiment done by me and Mr. Thrive and Survive on an earlier video. And yes, that's using the huge 100 times bigger than the Earth sun. So at this point, I will say thank you to Ruhif, because even though he caused this video to be 7 minutes longer than it would have been, he also allowed me to expose the idea that we can see various fractions of a degree below our horizon as not only erroneous, but completely irrelevant to being able to see both the sun and the moon in its peak positions at the same time. So, what say we zoom back in and discuss the refraction claims now? So as expected, many of the Ball Earth astronomy experts in the comments section appealed to refraction, allowing Bill and Jane to see the peak new moon while also each seeing half of the sun on their horizon. Wolfgang went all out, claiming that from a 500-meter high hill, they'd be able to see the entire moon once we added in refraction. Others suggested seeing various amounts of the moon due to refraction. But what surprised me, and I even asked them about it, is that not one of them went to the official standard refraction chart that they're always linking to us to calculate exactly how much of the moon we should or shouldn't see in that situation. And I found it very telling that they wouldn't make use of the chart that supposedly has this refraction stuff all figured out down to a gnat's ass. But Michael Dunleavy hit the nail right on the head. Can they both see the moon? Of course not, for the same reason they won't both see a solar eclipse. It will take a couple hours for the moon to move out of perfect syzygy so one of them can see it. That is exactly right, Michael. Well done. The moon, as we're seeing it in this diagram, is at peak new. This is 2 full hours after Jane could have seen half the moon on her horizon along with half the sun. And it's 2 full hours before Bill will be able to see half of it on his horizon along with half the sun. I'm going to do a separate video exposing the many things wrong with the idea that we see the sun and moon in refracted positions in the sky that aren't their actual positions. But even though Michael doesn't yet realize it, he has just single-handedly destroyed that silly idea already. And the best part is that I'm going to use Sly Sparkane, another Ball Earther, to drive Michael's point home. First, let me point out that Sly's animation of the Great American Eclipse of 2017 is to scale, and even has the unsubstantiated big-ass sun that the Ball Earthers crave. Now, as you're watching that moon orbit the Earth, ask yourself if Sly has depicted the actual position of the moon, or a moon that is refracted to a different position. Surely we can agree that he's depicting the moon's actual position, right? I'm just going to let this play out for a minute so we can all see that we're just watching a scale model of the moon orbiting the Earth. Nah, we don't need to see it again, Sly. Let's just jump ahead to the close-up. As you can see, Sly's already got Bill and Jane's horizon lines drawn out for us. Since they're both green, we'll just have to remember that Bill's on top of the Earth and Jane's on the bottom. Okay, the moon is right now at peak new. Since the moon is aligned on the vertical plane and the horizontal ecliptic plane, a person right here is in the pointy little moon shadow and can look up and see a totally eclipsed sun, right? Keep in mind that this guy is seeing the sun and moon in their actual positions because the light is hitting the atmosphere straight on. And where there is zero angle of incidence, there is zero angle of refraction, right? But what about Bill and Jane then? According to astronomer extraordinaire Nick Loam, Bill and Jane can each see half of the sun geometrically. When you add in refraction, they can actually see the entire sun on their horizons at the same time. So while Middle Earth guy is seeing the moon in its actual position, eclipsing the sun in its actual position, shouldn't Bill and Jane each be seeing the moon in a refracted position, eclipsing a sun in its refracted position? And think twice before you say the moon wouldn't refract out as far as the sun, because that'll come back to bite you on the ass in the last video of the series. In fact, let's just nip that in the bud right now. This is the moon in its actual position, right before it begins to pass Bill's horizon line, allowing him to see it. By the way, Bill and Jane are always on the terminator line for this exercise. Just imagine them traveling as fast as the Earth is rotating, so that they remain always at the terminator line, since we're trying to determine what they could or couldn't see from the terminator line at any given time. So had Bill been moving with the Earth, this would be the geometrical position of the moon right after it's set. But then there's the refraction, right? TimeAndDate.com says, because of refraction, the sun may be seen for several minutes before it actually rises in the morning and after it sets in the evening. This effect also has an impact on the time that the moon can be seen before moonrise and after moonset. So although the moon's actual position is below Bill's horizon, he can still see at least half of the moon above his horizon due to refraction. And that refracted moon has no choice but to be eclipsing the sun that he's also seeing on his horizon, right? So we have Bill and this guy both seeing an eclipsed sun from hundreds of miles away from each other. Here are a couple of clips from my interview with Arizona State University planetary scientist John Kristof. I will upload the entire uncut interview and link it in my next video, which will be the last in this series. But listen as he agrees with me and Michael Dunleavy that it would be 2 hours from peak new moon before a person on the terminator line would be able to see the moon.
I've got one last question then.
Shoot.
Okay, they can't see the full eclipse
They will-
at new moon. How far do you think, so let's say it's this guy, how far past peak new would you say? And
Well, you said it yourself. It's plus or minus 2 hours here.
at the point that somebody is here, not particularly this guy, anybody is right here,
Yeah.
where is the moon to where that guy that is there at that particular time could
Will
see
we see a
the
total
full-
eclipse?
Could see it, yeah.
He'll see it
How far off of noon?
So he'll see a total eclipse when if he's right on the edge, if he's at Terminator,
At Terminator,
then
right?
the total eclipse will occur at this farthest point at the -2, what we decided is the -2 hour mark.
Okay.
Here is the actual paper from that interview. Here is peak new moon, and here's the -2 hour mark that John was saying the moon would have to be before this guy on the terminator line could see it. If you haven't figured it out yet, a simple heliocentric solar eclipse in and of itself utterly destroys your claim that, due to refraction, we see the sun and moon in different positions than their actual positions. Just think it out like Dunleavy did. We can all agree that Middle Earth dude is right now seeing the actual moon totally eclipse the actual sun, right? But if we add just a little refraction into the mix, these guys will see a slightly refracted moon eclipse a slightly refracted sun at the same time Middle Earth dude is seeing his actual eclipse. And if we add a little more refraction due to an even higher angle of incidence, then these guys will be seeing a slightly more refracted moon eclipse a slightly more refracted sun, while the previous people are also seeing their less refracted and 0 refracted eclipse. So do you want to continue this pattern all the way out to the 2-hour mark, so Bill, Jane, and everyone in between can all be seeing a moon that is refracted to some extent, eclipsing a sun that is also refracted to some extent? Or are you ready to accept that the moon actually is a full 2 hours from either Bill or Jane's view when it's in peak new position, like I, Michael Dunleavy, and ASU planetary scientist John Kristof say? I hope to have the final installment of this angle series uploaded next weekend. For now, I leave you with this question. How many hours or minutes from peak new do you now say the moon must be before Bill and Jane can see it from the terminator line?